In section 820, we're looking at covalent bonds only. You will need a periodic table, so if you do not have one handy, you want to pause this video and grab one. All right, as you recall, covalent compounds, there are some subtypes. There are polar and nonpolar. So covalent compounds, which are known as molecular compounds, share electrons, but they may share them evenly or unequally. If they share them unequally, they were considered polar, and polar is 0.5 to about 2 difference in electronegativities. So they're being shared, but they're not being shared equally. We consider 0 definitely nonpolar, and then we also have a margin of error at 0.5 that we still consider nonpolar. When we have something greater than 2 difference in electronegativities between two atoms, that would be considered ionic, because the only way we're really going to have a difference of that much is if we have a metal and nonmetal combination. Metals have a lower electronegativity than nonmetals. So here's water, oxygen, and hydrogen. If you look at the electronegativity table, oxygen has a higher value than hydrogen. So what that means is electrons are being pulled towards oxygen. And so this notation is called a partial charge. This is a partial negative. This is a partial positive. You always put the partial negative on the atom that is more electronegative. And then by default, the partial positive would go on the other atom. We'll see this more in the last section, section 4 of this unit. This doesn't have any partial charges because we're talking about oxygen. There's 2 of them, so we know that it's equal, and this is a nonpolar molecule. So there's no pull towards one way or the other. A molecule is another term for a covalent compound. This is, we're not talking about ratio of ions like an ionic compound or formula unit, but rather a unit that can exist on its own. This is glucose, for example, and water. Those are definitely molecules. Notice this is not a molecule. This is table salt sodium chloride. This would be considered a formula unit. This is a little review from previous unit when we talked about, or we had to write a lot of formulas. So diatomic elements, have no fear of ice cold beer is a way to remember. Are 7 diatomic elements, and that means they occur in pairs bonded to each other in nature. And they are pretty much all of your halogens plus H, O, and N. Drawing Lewis structures. If you got the paper version of this, it is not included, so you may want to write this down. If you have the digital version, you should have this inserted in one of your pages. We're going to refer to those rules when we're drawing covalent compounds, the Lewis structures. So we always approach it systematically. You will need your periodic table at this point. We can have single, double, or triple bonds. So those are where they are shared. And then we also have lone pairs, which are unshared pairs. So H2, for example, what you're going to do is you're going to look at a periodic table. And if you notice, H has 1 valence electron. So we're going to figure out our valence electrons total to begin with. So this is number 1 here. This is how many electrons we can work with. So hydrogen has 1, there's 2 of them. So we have 2 valence electrons. And then what is our next step? Our next step is to have 8 electrons surrounding them except hydrogen, which we're talking about, so it only needs 2. We're going to space these out symmetrically with H's on the outside. That's not really applying to this case since there's only 2 H's. We also don't have a central atom, meaning the atom that we write down first and then build off of. I will mention that when we come across an example. All right, so H is just 2 H's. So you could just draw them horizontally next to each other, or you can draw them vertically. It doesn't really matter. And then what you're going to do is we have only 2 valence electrons to work with. We're going to always start with our bonded pair, and you can draw them in a pair like that in between the 2 H's. And that's all we have, but that actually just satisfies are hydrogens because they are shared, so it applies to both hydrogens. So sometimes they like to do this, especially at the beginning, to show that this H has 2 and this H has 2. Remember, hydrogen is good with 2. So that's it for that one. All right, water, H2O. Well, water, H has 1 valence electron, but there's two of them. So 2 times 1 is 2. Plus oxygen, if you look for the valence electrons on oxygen, is 6. So we have 8 valence electrons. And what we're going to do is, in this case, we do have a central atom. When we only have 2 atoms, we just draw them next to each other. But when we have more than 2, we're going to have something that we draw first, and then all the atoms come off of it. So H is never going to be central, because if you make it central, you're going to give it way too many electrons. Also, consider symmetry. Chemistry loves symmetry. So if you think about it, just aesthetically, what would look best? It would be oxygen in the middle with H's surrounding it. So make it as symmetrical as possible, and that's usually the way that it really is. All right, so we have this drawn out. Now remember, we have 8 valence electrons to work with. We're always going to assume a single bond, which is a pair of electrons, and we're going to put them between the 2 pairs of atoms that we have. So these are bonds. And we just used up 4, so we have 4 left. Now, hydrogen is good with 2 electrons. So you can see that it is good. But right now, oxygen only has 4. So it's not going to have any more shared, because we don't need to share anymore. And plus, we would give our hydrogen more electrons than it needs. So what we're going to do is we're going to put lone pairs, and these are unshared pairs around the oxygen. So I used up 8 electrons, but everyone is satisfied with all their outermost shells have what they need to be stable. Another way to draw these is lines. So it's up to you how you want to do it. Usually in the beginning, a lot of people want to do dots at first, and then they kind of get used to it and they start doing lines. Now the lines only apply to the shared pairs. You're not going to draw lines for those lone pairs. You just have to draw dots. Okay, here's another example, oxygen, O2. Now remember, that's just the same, so we're just going to draw them next to each other, but let's first figure out our valence electron. That's always what you want to do first. So your valence electron are 6. We have 6 times 2, we have 12. So 12 valence electrons is what we can work with. We cannot, by the way, we cannot use any more. We cannot use less. We have to use exactly the amount that we calculate. So draw 2 oxygen atoms next to each other. Then you are going to draw a shared pair. And by the way, pencil is always good for this, because you will sometimes have to change some stuff. So we have 2 here. Okay, and then we're going to assume the rest are lone pairs. So we have 2, 4, 6, 8, 10, 12. Okay, we ran out a pair. So let me do show how this one at least is satisfied. But this one is not, okay, because it only has 6 and this has 8. So we can't create more electrons, but in this case, and this is why we always approach it the same way, systematically, assume one single bond, which is 1 pair of electrons. What you're going to do is you are going to move one of these lone pairs, and you're going to make it another shared pair. So I got to fix my, oops. Let me erase this again. All right, so I'm going to redraw those those shared pairs. And now I can redraw my circles. So 2, 4, 6, 8, 2, 4, 6, 8. And that is going to be a double bond in this case. So only when I run out of shared pairs, I'm going to share more. So that's essentially what I'm doing. So this looks like this. If you want to use the lines instead of the dots that are shared. Again, we're going to have to use the dots when they're lone pairs. And you can see 2, 4, 6, 8 for this one, 2, 4, 6, 8 for this one. We always count this one for both of them because they're being shared. All right, carbon dioxide. We have carbon has 4 valence electrons. If look at your periodic table. Oxygen, there's 6 of them per oxygen. 6 times 2 is 12. So we have 16 valence electrons. Now, let me know, we should be looking at this if we need to. When you do the central atom, in this case, we do have a central atom because we have more than 2 atoms. It's always the least electronegative atom, so you can use your electronegativity table to figure it out, except if C is involved. So carbon, like things like to bond to carbon, and again, consider symmetry. Carbon is in the middle or central, and then you can put the oxygens surrounding it. And then we have 16 valence electrons, so we're going to create 2 shared pairs, okay, to surround our carbons. And then now we have 4 that we just used, so we have 12 more. So we'll just start going around the atoms as lone pairs. So 2, 4, 6, 8, 10, 12. All right, so notice I have my carbon is not happy. My 2 oxygens at this moment are, they both have 8 surrounding, but my carbon only has 4. So I don't not only need to share one more pair, but 2. So I can move them, but I can't create more. So I'm going to take 1 pair from each oxygen, and wouldn't have mattered how I drew these. I would be 2 pairs short no matter what. And I'm going to create 2 shared pairs. So now I did not create any more electrons. I still have 16, 2, 4, 6, 8, 10, 12, 14, 16, but I have 8 surrounding everyone. And that's really what you're doing, is you're making sure everyone has 8, except for hydrogen, because it only wants 2. And we're just rearranging them as needed. And this is how it would look should I have I want to draw it with these lines instead of dots. All right, our last one here, we have a triple bond actually. So sometimes what happens is we have to share even more. And for our level, we're only going to go up to triple bonds. So single, double, triple bonds, those are kind of the normal ones anyway. Nitrogen has 5. 5 times 2 is 10. So 10 valence electrons. We just only have 2 atoms here, so just draw them right next to each other. 10 valence electrons. So 2, 4, 6, 8, 10. Okay, now we have 2, 4, 6, 8, 10. We have 2 pairs that are deficient on this side. We're good with this side. So what we're going to do is we're going to erase from here, because this is where we have more. And we are going to share even more here. So 2, 4, 6, 8, 10. That's actually a triple bond. So I could draw it like this. And this is the only way I'm going to be able to satisfy it. Now, things are not normally going to want to form double, triple bonds unless they have to. So sometimes they'll be like, oh, this works out if I do a double or triple bond, but it also works out if I do a single. Well, single bonds is always going to be where it's at because that costs the molecule a lot less energy than having a double or triple bond. So 2, 4, 6, 8 for this nitrogen, 2, 4, 6, 8 for that nitrogen. All right, this is called VESPER theory. It stands for valence shell electron pair repulsion. So basically, it just determines the shape or geometry of the molecule, and that is in the next lesson, 8.3. So the nice thing about these lessons is they kind of build, and so you have to keep doing the same thing and just adding to it. So you either get better or it gets easy for you. What this means is that valence electrons want to be as far away as possible from each other. So they're going to deform the shape and create a shape where the electrons are as far apart as possible. And so, for example, like water, this is a bent shape, and then these are linear. Again, this will come in the next lesson, but just to kind of introduce, electrons like to be away from each other as far as possible. All right, try these out. Pause the video and try these before moving on. Again, go back to your rules if to go ahead and like systematically approach this. Use pencil, I would recommend, because it can get pretty messy if you use pen. And then once you try these out, check them by unpausing the video to see the work. All right, for HF, this is just two atoms, so we know we're just going to have them right next to each other as far as drawing them. But first of all, we have to figure out the valence electrons. Oops. So 1 for hydrogen, 7 for fluorine, that's 8 valence electrons. You're going to draw them right next to each other. Then you're going to do a lone or a shared pair between HF. And then remember, hydrogen is good with 2 electrons, so now we have 6 left, and you're going to put them as lone pairs around the fluorine. And then if it's helpful, go ahead and draw circles around where our electrons are surrounding the atoms. So you can see hydrogen has 2 electrons, and then fluorine has 8. I didn't use more than 8, and now I'm done. And again, you can draw it like this if you like, but you do have to put the lone pairs as dots. All right, carbon tetrachloride. All right, so carbon is 4, and we have 7 times 4, which is 28, 32 valence electrons. Carbon is always central should it be involved. Draw it symmetrically around carbon. You're going to do now your lone pair, or sorry, your shared pairs. So we have 8 surrounding. Right now, carbon is good. Now we have 24 more to go. So 2, 4, 6, 8, 10, 12, 14, 16, 18. Did I count wrong? 4 plus 7 times 4 is 28, 32. Did I? Oh, sorry, up here, that's why. All right, so I should have 32 total. And let me do my circles. So chlorine is good here. And then carbon is good. This chlorine's good. And this chlorine's good. And so is this one. And you can count these. You want to pause and count, but I know it's 32. All right, so our last one here, we have silicon dioxide. Silicon is 4 plus 2 times 6 is 12. So we have 16 valence electrons. Silicon dioxide, if you think about it, usually actually too, also another thing is the central is usually listed first, but again, go by symmetry. Silicon is going to be my central. Oxygen will be surrounding it. You can draw it vertically if you want. We have 16, so assume it's a single bond, 2, 4, and now we are going to go around 6, 8, 10, 12, 14, 16. Well, right now our oxygen's the way I drew it, and it doesn't matter how you draw it, but you're going to be deficient somewhere. Right now my oxygen is good on this side, this one's good, but notice silicon, we only have 4. So if I have 4, that means I have 2 pairs deficient. What I'm going to do is I'm going to move 1 pair from each oxygen and make it another shared pair. So I'm going to squeeze it in right here. So it would look like this. Should you want to draw the lines instead? So sometimes you have more than one double bond. Now the molecules are going to tend to form 2 double bonds instead of 1 triple bond. Remember that it does go kind of in that priority, like single, double, then triple. So I guess this is the key too. This is a little nicer looking, but you saw my process in case you needed that. And there's silicon dioxide. Resonance is just a concept. If you have like one double bond and it could flip around to another place, like you have more than one possible structure. For example, ozone is O3. If you were to calculate that, it's 18 electrons. And so it's going to be deficient one of the oxygens is going to be deficient on a pair of electrons. So we're going to need a double bond on one side, but you can double bond. You have two choices. So you see this double-headed arrow, that means it's just like it's dynamic, and this double bond actually keeps flipping around. And it'll just keep flipping around. And if you take organic chemistry, you will remember these arrows, things flipping around. So it resonates between structures. Polyatomic ions, because if you look at the structures or the atoms involved, they are all nonmetals, even though they have charges. So collectively, they have a charge, but they are covalently bonded, actually. When we draw these, you are going to do your valence electron total as normal. But then if you have a positive one, you will take away an electron. In this case, you have a 2 minus, and so we add 2 electrons. So N would be 5 plus 4 times 1 is 9. And then we'd actually subtract 1. So this is 8 valence electrons. So you can see 2, 4, 6, 8. And they also have this notation with, they put the brackets around with the charge, so it indicates it's a polyatomic ion and not just a regular molecule. This one, sulfur, is 6 plus 4 times 6 is 24 plus 2, because we have a 2 minus charge. So what is that? 32 valence electrons. And so that works perfectly around like that. And then you notice we have this notation that has the bracket with the charge. All right, last concept. I know this is a long one. Naming and writing formulas for covalent compounds. This has a different naming system than the ionic compounds. Ionic compounds, we have the crisscrossing and we have the polyatomic ions to worry about. This is a little bit easier because we are using just our Greek prefixes to indicate the number of atoms that we have in each element. And this is going to be binary, meaning there's 2 elements. So the only thing is you do not use mono for 1 on the first element. So like, for example, like CO, that's actually carbon monoxide, but not monocarbon monoxide. So that's just a big exception, but pretty much everything else just follows the system. Another thing is we do have an "ide" ending for the second element. The first one we don't. So P2O5, for example, di, you just find what 2 is, diphosphorus, and then pentoxide. Now it's not a huge deal, but like when you're not going to normally have 2 vowels next to each other, so it's not pentaoxide, it's pentoxide. If we have a separate vowel like triiodide, we'd have 2 I's next to each other, but sometimes we drop that vowel. Again, not like very serious if you don't remember to drop it. All right, so for example, to try these out, go ahead and pause the video and see if you can name these according to the rules here. And then you can check the key. Yes, I do not have a key. So this is called carbon dioxide. Again, no mono. 4 is tetraphosphorus decahydride. This is carbon tetrahydride. This is dihydrogen dioxide. And this is sulfur, not monosulfur, just sulfur hexafluoride. All right, and then you can go the opposite way. So this one even most people find easier because you are given this, and then you just have to come up, or I'm sorry, you're going to be given the name, you come up with the formula. So dichlorine monoxide, Cl2O. And you're not going to reduce or simplify any of these subscripts. That's something to remember because these are the true number of atoms that are coming together. So dicarbon tetroxide would be C2O4, for example. Go ahead and pause this, see if you can answer the last four, and then come back and check them. All right, hydrogen monosulfide would be HS. Again, see how there's no mono here, but there's a mono here. It's just a rule. Pentaphosphorus trinitride is phosphorus, but there's 5 of them. Nitrogen, there's 3 of them. P5N3. Sulfur pentoxide as SO5. And then silicon tetrafluoride is SiF4.